My plan for today is to talk about relative max and min, like subject to constraints, which is kind of what you were doing in lecture yesterday. And then to get a little bit ahead, because I'm not going to see you again until Tuesday. So right at the end of class yesterday, Dr. Thomas mentioned that there's another technique that we can use. We're going to get some practice with that today because it's definitely on the 5.4 homework. Of dealing with that constraint, we're really just going to take that constraint function, plug it into our other function, and then follow the same process we were doing a couple days ago. So I will do that first step, and then I will leave it to you all, give you a couple minutes to take our partial derivatives. So here I've conveniently already solved for z for us. I'm just going to pop that in. I would recommend just me, but if I had to do those partial derivatives, I would rather multiply that y through than do a product rule. Up to you. So I'm going to write that our function of just x and y would look like x cubed minus 27x plus 256y minus y to the fourth. So finding those relative extrema, we need to set the partial with respect to x equal to 0 and the partial with respect to y equal to 0 and do whatever kind of algebra we need to solve that. Between x and y here. So when I take that partial with respect to x, I just get 3x squared minus 27. When I take the partial with respect to y, I just get 256 minus 4y cubed. Setting each of those equal to 0. Over here, I can factor out a 3, and then I'd have x squared minus 9, which I can factor as x minus 3 times x plus 3, or just go straight to saying I know my x's are plus or minus 3. Over here, I'd probably personally factor out a 4. So that's going to leave me with 64 minus y cubed is equal to 0. I could factor that. I'm not going to factor that. That is a difference of perfect cubes. I'm just going to say I know that 4 is never equal to 0. And the only solution to this is y equals 4. So to go back to what we were talking about last time, I need something from this to be true and something from this to be true, because in order to be a critical point, I need both of those partial derivatives 0. So this gives me 2 critical points to check. I've got 3, 4, and -3, 4. Now, I should be careful here, especially thinking about your homework. That point should also include a z value. So I haven't gone back and plugged those in, but it shouldn't be too bad. So now we can do our Hessian, or the determinant of the second partials matrix, to determine which one of those is a minimum. If either one is a minimum, hopefully I didn't screw up. Hopefully they're not both saddle points. So let's see. My second partial with respect to x twice, you get 6x. My mixed partial with respect to x and then y looks like 0. And my second partial with respect to y twice, let's get that up. My second partial with respect to y twice is -12y squared. How'd I do? So if I am at the point 3, 4, then my Hessian, or the determinant of the matrix I didn't actually write, that part's 0 regardless of the point that I'm at. But at 3, 4, this would look like 18 times -12 times 16. I'm not even going to worry about calculating that. Regardless, it's going to be something negative. So I know that that's giving me a saddle point. And at my other point here, if I plug in -3, I've got -18 and then times -12 times 16. That is greater than 0. And then I'm going back and looking at the concavity in both the X and Y direction. And because they're both negative, I know I'm concave down in both the X and Y direction, and I must have been at a maximum. So it looks like I did mess up this problem. There is no minimum. Trying to find which point on this plane is closest to, if I imagine kind of the tip of my pen right here. So visually, our brains are pretty good at doing this. Our brains can kind of see, oh, the closest point on this plane is probably right about here. Mathematically, what we're doing when I'm talking about how close something is, we're trying to minimize the distance. And the hint that I gave here is the same hint that you actually get in the similar homework problem, where my hint is minimize the square of the distance, because the algebra is a lot easier. So my generic distance squared formula, I'm taking a generic point X, Y, and Z and looking for the distance to the point 532. I look at that and go, oh darn, I have too many variables, because our method for finding and classifying critical points only works if I have 2 variables in the mix. So now I'm going to have to get rid of one of those 3 variables, and it doesn't actually matter which one, but our constraint in this case is that the relationship between X, Y, and Z looks like this. It doesn't matter which of those variables we solve for, but I'm going to go ahead and solve for Z so that our partial derivatives are kind of our standard X and Y that are maybe friendlier to work with. So I'm going to call this function, I'm going to call this F and turn this into a function of just X and Y. So I'll have X minus 5 squared plus Y minus 3 squared plus, and then here I'm going to swap out Z. So Z is going to look like 15 minus 2X plus Y, and then I've got that minus 2 hanging out. I'll give you a minute to take the partials with respect to X and Y. Oh, good question in the chat. Yes, you can multiply those things out if you want to, or we can use chain rule. I for sure would use chain rule on this last one. If you want to multiply out the first 2, that works. You can multiply them all out if you really want to. Do you want a little more time to do derivatives? We've got it, got our partials? Okay. So my partial with respect to X I'm just gonna go ahead and use chain rule. So I have something in parentheses squared. I'll bring my 2 down. Technically, I should multiply by the derivative of the inside, but it's just gonna be 1 with respect to x. With respect to x, this whole middle term, the derivative is 0 because the whole thing is a constant. This has an x in it. So I'm gonna go ahead and use chain rule again, bring that power down, have all of this stuff in parentheses. And chain rule says I need to multiply by the derivative of the inside. And since we're doing this with respect to x, that looks like a -2. Doing the same thing for my partial with respect to y. That first piece of it, partial derivative is going to be 0 because we're doing it with respect to y and this only has x's. Next part, we'll chain rule 2 times y minus 3, new exponent is 1. For that back part, my chain rule is going to look almost the same as it just did for x. But now, if I'm multiplying by the derivative of the inside, again, thinking about the partial with respect to y, I would really just be multiplying by 1. Okay, now the fun part, the algebra. Because if I set each of these equal to 0, from looking at them, I can tell they're both going to be equations of lines. But I think distributing everything all out is our best way to get there. So I didn't leave myself a ton of space, but let's see if I can do it. So if I distribute this out, I've got 2x minus 10. I've got a 2 times a -2. So that's -4. So -4 times 15 would be -60. -4 times 2x would be positive 8x. -4 times y. And -4 times -2 would be positive 8. And that whole thing is equal to 0. Hoping I did all that right. So if I simplify that a little bit more, I've got a 2x and an 8x, so I will make that a 10x minus 4y. And combining all of my numbers, -10, -70, plus 8. So I think I'm at -62. Is that what you all got? Stop me if I made an arithmetic mistake. Or a distributing numbers mistake, it happens. Good? Okay, cool. And for the second one here, if I distribute everything out, I've got 2y minus 6, distributing my 2, so plus 30 minus 4x plus 2y and minus 4. So if I combine all of that together, I've got -4x plus 4y. I don't know. That started to look like a z to me. It's a 2. It's a 2. I crossed my z's, so we're all good. -6 plus 34, so that's, sorry, -6 plus 30 is 24. And then subtracting a 4 means I'm at 20. And conveniently, because my y's have the same coefficient and opposite signs, I'm going to solve this system by really quickly just adding the two of those together. And if I add those together, I am looking at 6x plus 0y minus 42 is equal to 0. So it looks like x needs to be 7. With any word problems, I definitely want to go back and read the actual question and make sure I've answered the question. Well, in this case, we were trying to minimize the distance. So all I did so far is find an X value. I haven't completely found the critical point, and I also haven't shown that it's a minimum. So I've still got a couple more steps to do. If X is 7, I can choose either of these equations to plug it back in to get the value for Y. I'm going to choose the second one just because the numbers are smaller. So if I plug in 7 for X, I would have negative 28 plus 20 would put me at negative 8. So if 4Y minus 8 is equal to 0, I think Y has to be 2. And I do not have enough space to do our second partial derivatives on here. I don't. Yeah, I do. I got this. I got this. We'll squeeze this in. So my second partial with respect to X, since I simplified fx down to just be this, looks like my second partial is equal to 10. My second partial with respect to Y twice, I simplified it down to here, so it looks like that's going to be a 4. And my mixed partial, if I start with my partial with respect to X and then take it with respect to Y, I would have negative 4. So there actually isn't anywhere for us to plug in our critical point, which is okay. We can still find that value of the Hessian, and that would look like 10 times 4 minus negative 4 squared. That is positive. And now if I come back in and I look at the signs for my concavity, because they're both concave up, I am actually at a minimum. I didn't mess this one up. It really is a minimum, but we have one last step, which is in order to give the point, I need an X, a Y, and a Z value. So I've got my X, I've got my Y, and I just need to plug that back in to come up with Z. If Y is, so if X is 7, that would be 14 minus 2. So now I'm at 12, which must mean Z is equal to 3. So my point for the final answer here would be 7, 2, 3. I'm trying to minimize, but I'm going to look at that and say, oh darn, I have too many variables. And if we have too many variables, meaning more than 2, the method we've been using for finding the relative extrema doesn't work yet. So I'm looking for a constraint that's equal to a number. And the only number we've been given in here is the 36 million cubic feet. Cubic feet are units of what? Since they're units of volume, that's going to be my constraint equation. And since we're talking about a box, the volume of that box should be the length times the width times the height. So I'm going to set that equal to 36 million. I probably should have rescaled the units on this problem so our numbers were not so large, but we're going to live. We can handle it. It doesn't particularly matter which letter I get rid of, but I do think that our brains work better if we solve this for Z and just work in terms of X and Y for the partial derivatives. So if I rearrange this for Z, I'm going to have 36 million divided by XY is equal to Z, and that we can plug in. Now I'm going to make the argument that there's another constraint that isn't explicitly stated in this problem. But if we're actually building a store, all of the values for X, Y, and Z have to be greater than 0. I can't have a we don't have negative height and length and width if I'm actually constructing something. So plugging that into our equation for the heat loss as a function of x and y becomes 12xy plus, now when I plug my z in here, that x and this x in the denominator are going to cancel. I'm going to have 9 times 36. Anyone know what 9 times 36 is? If not, I'm just going to drag it along with me. So I'm going to have 9 times 36 million divided by y. Again, plugging that in for z, my x is canceled, but not my y. $324 million. Which means my next piece, when I multiply this by z, my y's will cancel out, but not my x, so I'll have another 324 million. But this time divided by x. Do you want to take the partial derivatives on your own or do them together? My partial with respect to x. Derivative of 12xy is just going to become 12y. That's going to 0. And this one, if I think about, and I'm just going to quickly turn this into a 19a problem to illustrate. If I had 5 over x, I could think about that as 5x to the negative 1. And when I take that derivative, I would have negative 5x to the negative 2, which I could write as negative 5 over x squared. So that's how I'm going to write this next one. So I'm going to write this as minus 324 million over x squared. And that would need to be equal to 0. When I take the partial with respect to y, I get almost exactly the same thing. But now I get 12x minus 324 million, lost to 0, over y squared. They are not linear, but I am needing to solve this system of equations. So lots of options for how to proceed. Yes, so I could move this one over, solve it for y, and plug it in down here. I personally probably would like to get rid of the fractions on both of those. So I might choose to take that top equation. Imagine that I've moved all of this over and then multiplied both sides by x squared. So this would become 12y x squared equals 324 million. And this equation, again, I would move that over, multiply it up, and I would have 12x y squared is equal to 324 million. Maybe that's not any better. It felt friendlier to me to look at this way. But I still need to solve that system of equations. So either way, if I solve this one for y and then plug it in down here, or I solve this one for x and plug it in up here, it's not really going to matter which way I go. So let's solve that for y and plug it in down here. So I'm gonna have 12 times X. And then Y from the top equation would be 324 million divided by X squared, whole thing squared. Thank you. 12x squared, whole thing squared is equal to 324 million. This 12x, nothing is happening to. I'm just going to write this as 324 million squared. I'm going to write the bottom, the 12 needs to be squared, and the x squared needs to be squared. And then over here, I have 324 million. Now, part of the reason that I wasn't simplifying some of those numbers is just because I can see that some things will cancel out. So I can certainly divide both sides by 324 million at the moment, if we wanted, or I can multiply both sides. I'm going to clean up the 12 and the x's really quick. So I've got a 12 on top and a 12 squared on the bottom. So one of the 12s on the bottom can go away, and one of those x's can go away. So I'll just rewrite it. I'm doing an extra step that you may not need to write out, but I've got 324 million. That 12 has canceled out. I still have a 12 on the bottom, and I have an x cubed on the bottom. And then I'm going to get rid of the fractions. So I'm going to multiply both sides by 12x cubed. And I'm just going to, by the magic of an eraser, multiply both sides by 12x cubed. I'm going to divide both sides by 324 million. I'm going to divide both sides by 12. And as a reminder, the 324, if I go back in time to the beginning of the problem, that 324 came from taking 36 million and multiplying it by 9. So when I divide by 12, I'm going to choose to divide the 36 million by 12, which is going to take me down to 3. And then 9 times 3, I'm going to be at 27 million. So even though the numbers looked gross in the beginning, they do work out nicely. And our x here works out to be oh, sorry. Kill some zeros.
Wait, isn't it 300?
Yep.
Isn't it 30? Oh, yeah.
I think it's 300.
Mm-hmm.
Because if I did 300 times another 300 times another 300, I've got 6 zeros and 3 cubed is 27. So 300 feet Sweet. I'm not done with this problem. All we did was the algebra to come up with the X value at the critical point. Now I have to take that and plug it into one of my two equations here from my partial derivatives. Doesn't matter which one, but I need to plug it back in and get the Y value. And I'm going to go with the top one since the Y is not squared. So to get that Y value, I'd have Y equals 324 million, which I'm gonna again write as 9 times 36 million. Divided by 12x squared. And if we work out those numbers, I know the 36 divided by 12 takes me back down to 3 million. 9 times 3 million takes us up to 27 million. And if I'm dividing that by 300 squared, I think I'm going to get back 300. Because the top should be 300 cubed. And the bottom is 300 squared. So I'm going to get 300 feet there. And if those are both 300, we ought to be able to come up with a Z value. But do we want to check the second partial derivatives, or do we want to have faith that this truly will be a minimum? I'm good either way.
Wait, what?
Okay, let's do it. So if I'm going to check to see if this really is a minimum, I need to take those second partial derivatives. So if I come back up to my partial with respect to X, and I take the partial with respect to X again, this is like, I'm not going to do a quotient rule, but I am going to think about this as X to the -2. So then I'll be bringing down the -2 and I'll have X to the -3. So I would have -2 times -324 million. Yes. I would have -2 times -324 million times X to the -3. By the way, that's a negative times a negative, which is a positive number. If I take my partial with respect to Y twice, I'm going to get almost exactly, no, I'm going to get, well, almost exactly the same thing, but, oops, I lost a 0. Y to the -3. Again, I've got a negative times a negative. When I put those together, that's going to be a positive value. My mixed partial derivative is friendly. It is 12. So when I plug in 300 for X and 300 for Y, the overall value here is going to be positive, and both of these are concave up, which means I must have been at a minimum. Since I'm at a minimum, the only last thing I have to do is to finish finding those dimensions. So we had that X was 300 feet, Y was 300 feet, and Z should be 36 million divided by 300 times 300. Was T is equal to 12xy plus 9xz plus 9yz. And our constraint. And our constraint was that 36 million had to be equal to x, y, z. So if I rearrange that constraint function, I can say that's equivalent to G is equal to x, y, z minus 36 million. And the constraint is that G must be 0. So I've rearranged my constraint function so that it is something equal to 0. So what the Lagrange method says is now I've got these two functions and I know that they're related, right? Because one of these is a constraint on the other function. So if I've got these two functions that are related, then taking the partial derivative of x in one function should be proportional to taking the derivative of x in the other function. And we're calling that constant of proportionality lambda. So if I take the partial derivative of t with respect to x, and I take the partial derivative of g with respect to x, these two things should be related, as t of x is equal to lambda times g of x, where this is some constant of proportionality. And the nice thing is the partial derivatives aren't so bad. So let's go ahead and take our partial derivatives here and match everything up, like match up our x's, match up our y's, match up our z's. So when I take the partial of t with respect to x, I'm going to get 12y plus 9z. And I need that to be equal to some constant, and we use lambda because it's Lagrange. Name starts with L, lambda, L, cool, okay. And when I take my partial of g with respect to x, I don't have to drag around this giant number anymore because my partial with respect to x is just y, z. Now we're still going to have a bunch of algebra to do, but at least we're doing the algebra without giant numbers. Similarly, so this is from my partial with respect to x. If I do this with my partial with respect to y, my partial of t with respect to y is 12x plus 9z. And my partial of g with respect to y looks like xz. And if I match up my partials with respect to z, I'm going to end up with 9x plus 9y is equal to lambda times x, y. Now the last equation, right? I've got four unknowns here, x, y, z, and lambda. The last equation is always our original constraint equation. In terms of having four equations for four unknowns. But because my final answer that we were looking for is just values of x, y, and z, we're not looking for a value of lambda. What we can usually do, almost always, is to take the equations that came from our partial derivatives and eliminate lambda from them. Here's what I mean by that. I'm going to take each of those equations and solve them, like rearrange them to say lambda equals. So that top equation becomes lambda equals 12y plus 9z over yz. That second equation becomes lambda equals 12x plus 9z over xz. The bottom equation becomes 9x plus 9y over xy. And now because each of these are equal to lambda, I compare them up. So if I pair the top two equations up, meaning they're both equal to lambda, so I can set them equal to each other. If I pair these two up, then I've got, trying to make sure I got enough space here. So if I pair these two up, I've got 12y plus 9z over yz is equal to 12x plus 9z over xz. By the way, because this is referring back to our building of an actual store, I know that X, Y, and Z are all positive. I don't have to worry about potentially dividing by 0 here. Because if they were 0, we don't actually have a store built. So I already know that they can't be equal to 0. So right now, on both sides of the equation, I could get rid of a Z. Because if I multiplied both sides by Z, that Z is gone. And if I don't like fractions, then I would actually multiply both sides by XYZ. Really, there's no calculus going on here. This is like an all algebra all day kind of day. So if I multiply both sides by XYZ, I end up with 12xy plus 9xz is equal to, over here, my x and my z would cancel out, and I'd have a 12xy plus 9yz. I think I got that right. Oh, look. 12xy cancels out on both sides. And if 9xz is equal to 9yz, x equals y. Sweet. So I've got one relationship down. I know that x equals y, but I don't know anything about z yet. So I'm going to pair up the second two equations here and basically run through the same algebra steps. So if I pair up those second two equations, I would end up with 12x plus 9z over xz is equal to 9x plus 9y over xy. Multiply both sides by x, y, z. And the reason I'm multiplying by x, y, z is just to get rid of the fractions. You can you could instead like do stuff and drag around and common denominators. If I get rid of the fractions, I'm usually happier. So if I get rid of those fractions, here on the left-hand side, the x and z will cancel out, leaving me with just y. So I'd have 12xy plus 9yz. On the right-hand side, The x and y will cancel out, leaving me just with a z. So I'll have 9xz plus 9yz. And this time, the 9yz is what goes away on both sides. And I've got 12xy is equal to 9xz. My x's can cancel out. I can divide both sides by 3 and have 4y is equal to 3z. Which means I'm going to choose to write this as z is equal to 4y over 3. And the reason I'm doing that is essentially tying this back to 19b terminology. I have just made y my free variable, meaning I've written both x and z in terms of y, because my last step on a Lagrange is always to go back to the original constraint function to find the last variable. So if I go back to my original constraint function, we had 36 million is equal to x times y times z, but I'm going to write all of those in terms of y. So instead of x, y, z, that's going to be y times 4/3 of y. Or 3/4 of 36 million is equal to y cubed. You still have to deal with the big number in the end. But we swap out for different algebra in the interim.